recording going. But
Okay,
I think
it
looks like it's recording now, so we might as well start. Okay, so welcome everybody to our IR, Infrared Science Interest Group monthly webinar series. My name is Meredith McGregor. I typically moderate these things. I'm an NSF postdoctoral fellow at Carnegie DTM and a member of the IR-SIG Leadership Council. Thanks to everybody for joining us today. Since we don't have access to our usual WebEx connection, our speaker has kindly agreed to host this through Zoom. That means that most of our typical instructions don't hold since we don't have our WebEx set up. So I think for questions at the end, since we're a relatively small group, we sort of agreed that people could just unmute themselves and pipe up. And if that proves to be too chaotic, there's a function to raise your hand in Zoom, I believe, so maybe we can switch to that. But we'll go with just speaking up and seeing how things go from there. So I think that's basically it. And with that, I will just introduce our speaker for today, which is Professor Sunil Golwala from Caltech, who will be talking about the Leighton Chajnantor telescope. So Sunil, you can go ahead.
Okay, thanks. Thank you, Meredith, and thanks to the IR-SIG leadership for providing this opportunity. So the intent here was to try to update the community in whatever way possible on the status of this project and to kind of engage interest and also get input on means for community participation. We are leading up to an NSF MRI proposal next week, so that was kind of the immediate impetus, but it's obviously a longer-term program. Okay, so I'll jump in. So this is about the Leighton Chajnantor telescope. I've shown the participating institutions at the upper right. So it's Caltech, and then our Chinese partners are the Chinese Academy of Sciences, South American Center for Astronomy, and Shanghai Normal University. And then in Chile we have Universidad de Concepción. And on the lower right you can see the planned site. It's the old CBI site inside of Alma, and I'll say a lot more about that as we go on. Okay. All right. So here's a quick overview. I'll give you a very brief one-slide summary of the project, and I'll go over a bit of the CSO history to show you how we got to where we are, and then I'll talk about the concept for LCT, the main science opportunities, and the status, and including some discussion about ideas for community participation. Okay, so this is the basic summary. So the idea is to move the 10.4 meter telescope of the CSO, the Caltech submillimeter observatory, from Mauna Kea to the CBI site inside of Alma. It's an 11 micron RMS telescope, so it's one of the very few existing telescopes at this diameter and that accuracy. So it provides good efficiency at 350 microns, so it's a fairly unique capability, and then it has many other capabilities. We don't plan to bring the boat of an enclosure. We'll plan to build a new simple enclosure just to roll off the telescope for operations. And then I think the key change in the way the observing would work is that it's really a focus on enabling large projects at the sort of 1,000-hour level that would not otherwise be possible at a general purpose observatory, and making use of cutting-edge instrumentation. So motivating people to build very exciting instruments because they can get large amounts of time to do really compelling projects. There's also a plan to allow community access for technology demonstrations, and then possible ways to allow PI nights for the US community. The partners, of course, they will sort of partition the time between surveys and PI nights. The operation will be fully remote, and I'll talk a little bit about that later. And then we expect the Chilean and Chinese institutions to take on a lead role in the operation. So you can see the names of the leads at the partner institutions, two of which, Zhang Wang and Rodrigo Reeves, have a history with Caltech and with Owens Valley. So there's a kind of a long historical linkage. Okay, so I'll go back over a little bit of the history of the CSO, just for those who don't know it. I think it's actually very interesting. So the CSO grew out of an effort back in the 70s that was started by Leighton at Caltech to open up the molecular ISM, and this was in parallel with work at Berkeley and other places around the world. So they initially proposed a 3-element interferometer at the Owens Valley for millimeter wave operations, but they all along had the idea to build a submillimeter telescope in the long run. And the key thing was the development of a relatively inexpensive way to build a 10-meter diameter dish capable of the surface accuracy you need for these wavelengths. It's kind of a remarkable thing. These things were built in the high bay at Caltech on this crazy air bearing by Leighton and lots of undergrads. And when this effort was underway, Leighton drew Tom Phillips from Bell Labs, where he developed the SIS tunnel junction, and brought him in to try to start up the receiver end of the work to provide the receivers that we needed to do this opening up of the millimeter and submillimeter. The CSO itself was not started until the OVRO interferometer, which was completed, which had some delays. But the CSO started construction in 1984 with NSF funding, and then first flight in '87. So you can see this is the surface of the dish being cut with a parabolic cutting blade at Caltech, and there's Leighton and Phillips standing on the dish. Okay, here's some pictures of the site and some of the history. So you can see the site down here in the submillimeter valley that was at the time totally unoccupied. This is Leighton driving a stake in at the site that was going to be the place for the telescope, and then you can see the dome partially under construction, and then finally the dedication ceremony. And then here's the completed telescope, and Leighton and Phillips shaking hands at the inauguration of the telescope. Okay, I'll go back over a little bit of science history, not because it's incredibly relevant for looking forward, but because it just gives an idea of what's been done in the past. So during the 90s, the focus was really on the heterodyne instrumentation that Phillips was brought to Caltech to develop. So doing the first submillimeter local ISM line surveys, searches for lines in nearby galaxies, seeing that neutral carbon was omnipresent, studying turbulence in the ISM, and also understanding the atmosphere in the submillimeter, which this is one of the first opportunities to do so. So you can see these line surveys that were done across many of the submillimeter bands, just revealing this forest of lines. And then from this paper by Phillips and Keene in '92, sort of a summary of the most important lines in the submillimeter. Moving into 2000s, technology advanced, and the first large continuum arrays became available, and also the heterodyne receivers were improved. The main improvement there being the switch from tuned operation to tunerless wide bandwidth receivers that were much easier to use for users. But then I think the big advance was the bolometric array, so the 350 micron array SHARC-2, which was studying an important SED point for dusty star-forming galaxies at high redshift, studying sources on our own galaxies, looking at debris disks, and then there's the polarimetry with the SHARP optics module. We built a 1 and 2 millimeter camera BoloCam, which was used for a variety of extragalactic continuum surveys, and also a galactic plane survey, studying about a half of the galactic plane, and also opening up SZ imaging of individual clusters. Z-Spec was a bolometric spectrometer, low-resolution spectrometer intended for searching for CO and C+ in high redshift galaxies, and also looking at nearby galaxies. And then Zeus was also a low-resolution spectrometer built by Gordon Stacy, now for the shorter submillimeter windows, looking at C+ higher at more moderate redshifts. So I'll just kind of jump through a few of the exciting results from that time. So there was a lot of work on hydrides, trying to understanding deuteration in the cold dense ISM, finding surprising amounts of things like ND3. And then this is something that Derek can comment on. There were measurements of comets, trying to look at HDO to try to understand the D to H ratio in comets, the water in comets, and seeing whether comets could have been the source of water on Earth. And so that was an interesting story where it initially looked like it matched up, and now maybe it's not matching up. But again, an important measurement. With SHARC-2, I think a couple of the major efforts were measuring the 350 micron point on the dusty SED for high redshift galaxies. So on the upper left here is a sample of dust obscured galaxies detected by WISE, where the 350 micron point is really telling you what the dust thermal emission is separated from the AGN emission. And then here you can see a couple examples of highly lensed submillimeter galaxies where, again, the 350 micron point is critical for constraining the shape of the SED. And then over on the right is one of the very nice polarimetry measurements done with SHARP, the module that Giles Novak built at Northwestern, showing the correlation between the polarization direction and intensity and the structure of this shock from winds from OB stars. Okay, this is a very nice spectrum from Z-Spec of a lensed Herschel spire source. So you can see it extremely high redshift, C+, high JCO, whole bunch of molecules. So really opening up the study of the ISM at high redshift with these low resolution spectrometers that were very sensitive because they use bolometers. And then we did a galactic plane survey with Bolocam, which I think has had a lot of legacy value. You can see here on the upper left the coverage, on the lower left, zoom in on the CMZ, and then on the lower right, the follow-up data finding good velocity measurements for lots of sources in BGPS. And then we also did some interesting things with clusters, making sort of a gallery of clusters for one of the first times, looking at massive clusters, and then detecting actually the kinetic gas-Z effect in a subclump moving in a cluster that consists of 4 subclumps moving at high velocity as they collide and join together. Okay, and so as we entered the 2010s, there was continued exciting new instrumentation development. Kinetic inductors, inductance detectors had been invented about a decade before, and they were just now at this point coming into implementation in real instruments. There'd been a lot of work on using superconducting microstrip line to really open up lots of new ideas for what you could do for detectors at sub-millimeter and millimeter wavelengths, essentially letting you do things that you would normally do in the radio now at shorter wavelengths, like making filter banks, phased array antennas. So there were a number of instruments that were started to be developed at the time. So we built MUSIC, which was a pathfinder using kinetic inductance detectors and many of these microstrip line techniques to build a 4-band camera covering 4 bands all in the same focal plane. MACO was a technology effort toward developing 350 micron kilopixel arrays using direct absorption kinetic inductance detectors. And then SuperSpec is an ongoing effort to develop essentially something like Z-Spec, but now in a very compact format so that you can have that many pixels across a focal plane. So sort of spectrometer on a chip technology. And there are other groups developing similar kinds of concepts with different architectures. Okay, so let me just take a stop there and offer the chance to ask questions if there are any. I imagine this is things that most of this audience actually knows already. Okay, all right. So now let me kind of go into the modern day. So as of 2010, CSO is still quite a vibrant observatory. There was you can see from the publication rate that it is fairly constant at a sustained level back since 2000. There were lots of new instruments in development, and we were really preparing to hand off from CSO to CCAT. But then a number of things happened. We perhaps unwisely announced decommissioning in 2009 before CCAT was really on a complete trajectory. And at the time, the announcement was that decommissioning would begin by the end of 2016. Our proposal for continued NSF operations was declined in 2011, and a couple of years later, the URO program basically ended. And then the planned handover to CCAT ended because the MSIP proposal for CCAT was declined and the consortium sort of fell apart at that point. And so the CSO suspended operations in 2015 due to a combination of lack of funding and the need to actually begin decommissioning soon enough. But there remains strong motivation to find a path to using the dish and the instruments because, again, there was a lot of effort in developing new instruments that would provide new scientific capabilities, rendering the observatory of continuing relevance. And the telescope itself is a fairly unique thing. It's an 11 micron RMS 10-meter telescope, and there are only 2 or 3 on the planet with that capability. So, and there was no, especially the other one is Apex, and then CCAT-P is the third one coming along. So there really isn't a path in the US right now to such a single dish capability. So we thought that maintaining this resource was important. And then also we foresaw, in fact, we saw from operating the CSO after the NSF funding that it was very, very possible to reduce operating expenses by engaging in fully remote observing. And all the observing we did during the post-NSF period was essentially remote from your home office in the middle of the night. So that was able to knock down the operating expenses substantially. Okay, so this kind of leads us into the plans for the Leighton Chajnantor telescope, LCT. And again, the key motivation here is that the technology continues to move incredibly quickly. So you may think you have an old telescope, but much like optical telescopes like Palomar, it's a light bucket. And if you can develop new technology that uses that light bucket in a new way, you can do exciting things. So the classic technology of SIS mixers has improved over time because with wider output bandwidth and digital spectrometers, so really allowing you to cover more spectrum at one time. But then I think most exciting is the development of these multi-band imaging arrays and focal plane array spectrometers that significantly multiply the effective time available. and provide, simply reach to new kinds of science that wasn't possible earlier. The 350 micron field of view of the CSO was never even close to being filled, but now the technologies exist to make that possible, which would exceed Scuba 2's 450 micron capability, essentially increase the mapping speed at 350 microns by a factor of 40. And then there's, again, exciting developments. There's work on superconducting parametric amplifiers that might get us quantum limited detection all the way into the terahertz. So that would be an incredible thing, to be able to build focal plane arrays with quantum limited amplifiers all the way up to 850 gigahertz. Obviously, everybody knows that Chile is a better site, but it's well quantified at this point. The opacity is about 1.5 to 2 times better, and that also factors into sky noise. As I mentioned before, the telescope remains the highest surface accuracy, US accessible 10-meter aperture. The 11 micron surface was in fact better than APEC until its recent upgrade, which just has happened in the last couple of years. And I think CCAT-P coming along is the only other telescope with comparable surface accuracy. And then because of the decommissioning, and I can talk more about this if people are interested, we really have a deadline that once deconstruction begins, it's extremely unlikely we would be able to retain the telescope. And that's currently planned for early 2021. So we have effectively a deadline for finding a way to make use of this telescope. Otherwise, we lose it. We can modernize the way the telescope operates. Currently, the fastest scanning is a few arc minutes per second, but that's really a function of the motors, not of the telescope stiffness itself. Dave Woody firmly believes, and we're doing FEA work right now to check this, that we can scan the telescope faster and it'll maintain surface accuracy and pointing. It's really just a matter of upgrading the motors and the servo system. The field of view is quite useful. So we maxed out the field of view with the last millimeter wave camera at about 14 arc minutes. And that same optics provides a 7 arc minute field of view at 350 microns that was never utilized. That would provide a roughly 30 times gain in area over the current Shark 2 camera. And then optimized detectors would give you another factor of about 1 1/3. And then there's just the historical thing that the user facilities it's hard to do very big programs on user facilities. So if we instead orient this more toward large programs, that may enable new science that you couldn't do with less amounts of time. So I'll talk about the science in a little bit, but things like C+ tomography, very deep integrations on clusters, 350 micron surveys that weren't possible before. And then everybody, I think it's obvious that taking preparatory data for ALMA or complementing ALMA with data with 10-meter single dish would be very useful. Okay, so let me just quickly go over the historical and the plans for the instrumentation suite, since that's sort of the key to why an old telescope can continue to be exciting into the future. So what's shown here is the instrument suite that we had operating at the tail end of operations on Mauna Kea. So we have the heterodyne receivers covering the 4 atmospheric windows from about 200 through 700 gigahertz, and with varying resolution depending on the output FFTS. We had Z-Spec covering the 1 millimeter window fully at roughly a resolving power of 300. And then we had 2 continuum instruments, music covering from 150 to 350 gigahertz, and then Shark 2, which would cover either 650 or 850 gigahertz, and then it had the polarimeter module. And here's where things are located, and I think the key thing to take away from this is that the way the telescope is set up, you can have multiple instruments on at the same time with a fairly easy switch between them. So there's really a good ability to take advantage of weather conditions and to maximize the utility of the observing. So there's a large Cassegrain focus with relay optics, so that's where the large cameras sit. So this is music sitting on the Cass focus. Over on the left is one of the Naismith foci, and that has all 4 heterodyne receivers in it, and it's completely switchable between them remotely. And then over on the right side, there's another Naismith focus where where Shark 2 and the bolometric spectrometers typically sit. And then there's a relay optics cage sitting back down here that you can't see that allows you to direct the beam either to the left, the right Naismith, or the Cass, and it's also remote operable. And it's a matter of about 5 minutes to switch the mirrors. So you can really respond to observing conditions and use the instrument that's most appropriate for the observing conditions. Okay, so the near-term plan for the instrumentation. So what we would have on the telescope at first light in Chile would be the existing suite of heterodyne spectrometers, possibly upgraded from DSB to 2SB. That depends on how quickly we can make that progress. There's the instrument called Time. This is a 16-pixel resolving power of 100 spectrometer in the 1 millimeter window that Jamie Bach and Matt Bradford are developing, primarily for C+ tomography at high redshift, but it also will do very nice measurements of the CO, sort of CO population as a function of redshift. And then there's a parallel development of super spec at somewhat higher resolving power, more focused on 1 to 3 pixels, looking at individual objects, but also very compelling background limited technology for eventually filling fields of view with spectrometers. Music will extend to 100 gigahertz and 405 gigahertz, so it'll provide full coverage of the millimeter wave bands. And then it's expected that our partners in China at PMO would be able to implement a modern 850 gigahertz heterodyne receiver. So really, oh, and I don't know why I forgot it, but Shark 2 will obviously be will continue to be available, and at the new site, there'll be a substantial improvement in sensitivity thanks to the atmosphere.
Sunil, this is Mike Zemkov. Sorry to jump in. Are you going to talk about the status of NACO at all?
That'll come up in the next slide.
Thanks.
Okay, so then obviously, since the technology is so important, looking for the long term and what we might do in the long run is critical. So I think with music, about the only thing that could be added is a polarization. The detectors are polarization sensitive, but adding a wave plate would improve the systematics. And then we've effectively maxed out what we can do in continuum at millimeter waves. Technology like MACO, where that was a path toward kilopixel arrays at 350 microns, it would be very natural to build a successor instrument that would use the entire 350 micron field of view. And as I mentioned before, it's about a 30 times increase in field of view and a 40 times increase in mapping speed, over Shark 2. So that would, I think for the first time enable decently large 350 micron continuum surveys. It's expected over time that the super spec and time technologies will advance, and so in the long run, in the extreme long run, a resolving power of 1,000 integral field unit covering part or all of the field of view is technologically feasible. We have to figure out whether that's obviously optimally scientific, whether it's scientifically optimal, given that the depth you can go to with a 10-meter telescope is perhaps not quite as good as one would like. But it's certainly a path. And then I think the quantum limited kinetic inductance pair amp could really just open up heterodyne spectroscopy over this entire frequency range at significantly better sensitivity, and just a whole new ball game there. And there's again no reason that those things couldn't be turned into focal plane arrays. In fact, much more easily than current SIS or HEB mixers. So that's I think an exciting prospect in the long run also. Okay, let me talk briefly about the site. I know many of you know about how good the site is, but a couple of statistics. So again, the opacity, it's about 1.5 times better at 350 microns. So you could get Mauna Kea-like conditions up to about 40 to 50% of the time, or if one restricted the 350 micron operation to the best 25% of the time, like we did on Mauna Kea, sensitivity is appreciably better. And even at 225 gigahertz, capacity is about 2 times better on average. And we showed, about a decade ago that the sky noise tends to scale roughly linearly with the PWV. So you expect about a factor of 2 improvement in sky noise RMS from going to the better site. So, even the same telescope and same instruments, you gain a factor of 2 in sensitivity, a factor of 4 in integration time. So that's already pretty exciting, even if you didn't upgrade the instruments. It's doable. We know that you can move these telescopes, and in fact, they're almost to some extent designed to be transported relatively easily. So the move of the Owens Valley dishes up to the Karma site and then back down, that was all done by simply separating the primary from the pedestal and then mounting the primary on a trailer. And once you reassembled the telescopes at the new site, they started out at 50 microns RMS, so very, very close to their final accuracy, and a fairly modest effort to tune them to their final shape. And this is a really key thing. We're not rebuilding the primary from scratch. It's a relatively simple process to reassemble the telescope and get it tuned up. And then the move of the ALMA prototype antenna to Kit Peak shows just one example of how you could move a primary as a single piece. We, in fact, had Eric Nichols do a study for us to develop a full move plan surveying the whole path and basically convincing ourselves that we can do it for a reasonable amount of money. The site is the old CBI site. So zooming in, here's a view of the plateau where ALMA is, and then the top view here. And then zooming on ALMA, here's the array center, here's the AOS, and then the Caltech site, or the CBI site, is right here, about 300 meters away from a couple of ALMA pads. So the access is very good. It's just past some ALMA pads, and there's a road going right up to that point. This is what the site looks like currently. So here you can see, this is a picture actually of the former CBI/Quiet Mount with clamshell on it. So there's trailers surrounding it. There's a foundation pad that, and then there's an electrical line that goes out to a pair of diesel generators that sit a couple hundred meters away. And then here's the road out to the nearby ALMA antennas going in this direction. So you can see the site's fairly well developed. There's the containers that are there provide a lot of existing resources. So there's a couple of containers that are not only heated and lit, but they have oxygen. And then there's a couple of containers that are heated and lit, but don't have oxygen. So there's ample space there for the control of the telescope, and also for the compressors for all of the coolers. There's existing diesel generators that will either need to be refurbished or replaced, and then there's an electrical line that leads from them back to the site, and there's an existing tank. So again, lots of infrastructure is already in place. I'm not going to go through this in detail. This is sort of our science matrix for the key programs. The five key programs that we've come up with are so the C+ tomography into the epoch of reionization. So it's expected that time with 1,000 hours would be able to detect the power spectrum of C+ at redshifts of roughly 5.3 to 8.5 with decent signal to noise. Measure the integrated star formation rate history at high redshifts, and then also look at molecular gas at low redshifts using CO. So that's a roughly 1,000-hour survey. There are a number of measurements of the IGM, ICM, and CGM in clusters that we expect to do with music. So a survey, extremely deep survey of 1,200 clusters, seeking to look at the thermal SD effect and look at non-thermal pressure due to unvirialized material, and then to actually look at the velocities of the ICM using the kinetic SE effect like we did in that Pathfinder measurement with Volocam. It looks like doing submillimeter transients would be very interesting. There have been recently discovered transients that are quite bright in this millimeter, easily detected in about 20 minutes at about 1 millimeter wavelength, and then definitely worth follow-up with Shark 2 in a few hour integration sort of once a week. And we expect something like 5 to 10 of those per year. So these are either moderately relativistic supernovae running into a dense circumstellar medium. It's expected that low luminosity GRBs would also have similar brightnesses and be detectable. We plan to pursue some of the measurements that were done with Shark 2, but more aggressively on high redshift galaxies. So for example, measuring the 350 micron and millimeter wave fluxes for all of the 500 W1, W2 dropouts from WISE that should be accessible. This would provide a nice measurement of the star formation rate as galaxies evolve through the AGN and quasar phase, really kind of homing in on that part of the evolution of galaxies quite precisely. We can look at magnetic fields using Shark 2 and music in polarization mode. Again, probably more aggressively than we did with CSO, so a really large survey of order 100 Planck sources and bridging the scales between what Planck measured on sort of many 10 arc-minute scales down to what ALMA can measure on sub-arc-minute scales. And then looking at dust grain sizes via measuring dust SEDs and the emissivity power law, trying to constrain the size of grains in the ISM. So that would come out of a few 100-hour survey of the galactic plane, deeper than what was done with Volocam and Apex. So the idea here is a handful of these sort of 1,000 to 1,500-hour surveys, and that we'd have something like 1,200 to 15 hours per year available for surveys. Those could be completed in 3 to 4 years' time. Obviously, you get a lot of targets out of those that would be interesting for ALMA follow-up, perhaps new classes of targets. And then these surveys, they'll get replaced and evolve as the instrument capabilities grow. And that's an absolute necessity, that we keep on developing instrumentation so that new surveys can be done. And even the PI time, the single few night projects that will occupy the rest of the time are going to be great for complementing and preparing for ALMA observations. So we think that by evolving the technology, this remains an extremely compelling telescope. Okay, let me talk a little bit more about the project status at this point, but actually let me stop again and ask if there are any questions about the science plans, the instrumentation. Okay, I'll go on. Okay, so the roles for the project are 2 partners are Shanghai Normal University and Universidad de Concepción. And the Shanghai Normal effort is kind of the agent for that is the CAS office in Chile. So they effectively execute much of the work that is funded by Shanghai Normal. So they'll be taking the lead on the site infrastructure and this design and construction of a new enclosure. In fact, we have a contract out with M3 right now to do a design study for a simple roll-off enclosure where we'd be operating the telescope out in the open without a dome and then roll over only for sun and weather protection. Concepcion plans to be the operations lead, so they would have the technical director, the observatory office, and the technicians and engineers would be sited there, traveling to the site on a regular basis. Caltech, in fact, plans to some extent step away a little bit from day-to-day operations, handing that off to Concepcion and to Casaca, but to continue to do instrument development, to contribute to the development of the scientific program, so that we have this facility available for continued new science and new technology. And then part of the effort is to effectively hand off the receiver work to Shanghai and Concepcion. There's clearly continuing developments that can be pursued there, and so that's a natural place for them to build up their capabilities. So, in fact, we've had one of the staff from Shanghai Normal in the lab here at Caltech, helping Frank Rice to test the 230-460, confirm that it's still operating, and in fact, do the first test of Jacob Cooey's 345-650 focal plane that never got fully built up into a receiver, and those both are all looking very good. And so we plan to ship off these receivers to them for full switch over to dry cryostats. And then in the long term, jointly with Purple Mountain Observatory, we hope to expand the heterodyne suite and eventually do the parametric amplifier implementation. Okay, here's a summary of the project progress and status. So through a bit of luck, Tony Reed had midwifed this collaboration, putting me in contact with Zhang and Rodrigo in late 2015. In 2016, we wrote a 100-page CDR, mainly to make it clear what we wanted to do, because we'd been talking about it, but there wasn't any concrete plan until we wrote that. And we also got the estimate for the move cost of roughly 1.4 million for moving the telescope, which is not unreasonable. In 2017, Shanghai joined as a Chinese university partner, and then we submitted our CDR to ALMA, and this was kind of a key step, confirming that we would be able to use the CBI site. And so far, all signs look good on that, and we're working with them to fully obtain access to the site. And then activity ramped up a lot in the last year because we were able to hire a project manager, Gary Parks, who some of you may know from Herschel and Planck, and others of you may know from ALMA. So he's been developing a full cost and schedule estimate over the last year so that we have a strong basis for writing proposals. We obtained a key approval from the foreign ministry that lets us bring everything in without tariffs and effectively kind of gives official status of the project in Chile as a continuation of CBI. Shanghai received about half of the funds that we need, and it's kind of been elevated to the level of a national project. It's interesting that our status in China is effectively more official than TMT even, and so that's a good thing. And then we've been talking with CONICET and now at least have informal agreement on the terms for CONICET approval, 10% of the time plus a couple of other things to provide in exchange for access to site. And so we're preparing to submit MRI and mid-scale RI proposals to complete the funding for the move. Okay, so in terms of the funding and the community participation, so we put in a few $100K to get this far, to do the full costing, to do some of the estimates of costs for the most critical steps. We estimate the whole move and recommissioning and essentially getting ready to do science will cost about $8 million, which about half is in hand. There's going to be manpower contributions to cover part of that. And so obviously we're writing a proposal to cover the other half, and I'll talk about the exchange for data in a second. We estimate that for operations, it'll cost about $1 million a year. So that's going to be partially covered by in-kind manpower from Casaca, which is an office in Chile of Chinese Academy of Sciences, and Concepcion. So much of the manpower will be local in Chile, obviously, and then cash contributions from Shanghai. And then here's kind of where the natural discussion of community involvement is. So obviously we're proposing to NSF, and so we expect to provide something in exchange for that. So the obvious thing to provide would be access to the data from the surveys in exchange for the NSF funding. And then there's the possibility of continuing involvement by continuing support. So two ideas we had were providing technology demonstrator nights. So essentially anybody who's funded by NSF, ATI, or NASA, APRA, or SAT, they can bring an instrument to LCT for a few nights to get on-sky testing. And that we could imagine providing for something at the level of 100K per year for 10 nights. And then if there's interest in the community on science participation, one might imagine sort of a 300 to 400K per year investment by NSF, either for just open time, PI time, that kind of in the original mode of the CSO operation, or survey participation, being able to actually lead and participate in the development of the surveys and not just have the data products, or some mix of the two. And then in parallel, I think we'd welcome people building instruments and essentially doing an exchange where we provide a certain number of nights for the instrument to the PI in exchange for making it available to the user community and providing some level of support to the user community. So these are just thoughts, and again, one of the reasons to have this call was to get some feedback on these ideas and what people might be interested in. Okay, so that's all I have. So I think I'll just end by saying that we have a long and accomplished history of opening new windows and doing a lot of exciting instrumentation development. We have a deadline for the continued use of this telescope. It's about a couple of years. So really, we're approaching the last year of proposals that we could realistically submit to get action before the telescope would have to be removed. And we're moving forward aggressively with LCT. We've got a full project plan, budget, and schedule. And I think once we're able to get the remainder of the funding in hand, we'll be able to move forward quickly. And now is a good time to talk about opportunities for the community to be involved and be able to make use of this facility once it's up and running. Okay, so I will stop there and ask if there are any questions, and also specifically for input on these ideas for community participation.
Okay, great. Thanks, Sunil, for a great talk. So I said this at the beginning, but why don't we just have people unmute themselves and speak up if they have questions or comments or thoughts? I think we're a small enough group that should be reasonable.
So Doug Johnstone here, I have a question. I found it a great talk, by the way, but I just found it a little hard to follow. Your highest frequency camera at the moment, Sharp 2, what is its field of view, and what are the prospects for its field of view being bigger given what you're asking for?
Good. So the current field of view is 2.3 arc minutes square. So it's really not big enough to be a survey camera currently. So all of the the first flight science programs we have planned with Shark 2 would be a single object photometry follow-up where you're pointing at a known source. The field of view, we have optics that provide a field of view 30 times larger. So that's essentially an opportunity. There are a few paths to getting there. One path is PMO has had consistent interest in developing 850 gigahertz continuum detectors in addition to heterodyne. So some sort of partnership with them. If there is someone in the US community who's interested in pushing one of the existing technologies to an instrument of that size, I think we would welcome it. There's not an obvious person at Caltech who wants to lead that effort, so it's really kind of a community opportunity. I think the technology is there for doing that. It's a sufficiently small scale up from what's been made that you could realistically propose it at the few $1 million level, but we need to identify someone who's going to take the lead on that.
Thank you.
This is Jens. Thanks for the presentation, Sunil. Can you go back one slide?
Yes.
So concerning the community involvement ideas, you have there spelled out so and so many nights for so and so much money. So is the idea that this would be money which would have to be raised by a PI, either bringing an instrument to the telescope or coming for an own observing, science-driven observing program to the facility, or would this be covered by the NSF? That I didn't understand.
Okay, so that I think we haven't sorted out. I mean, if for example, NSF funding were put into place so that there's essentially something like 30 nights a year of open time, then someone who builds a PI instrument could very well just propose for that open time. So then they don't have to pay for the nights. Obviously, they need to get their instrument to the site, and then we can assist with getting it mounted. So it would be kind of a matched funding where the nights would be available already, but just like in the era of the CSO, you had to pay the cost of bringing your instrument to the telescope, and then we would support getting on the telescope and making it possible for you to observe. But these are, and let me just make it clear, I mean, these are disjoint to some extent in that there could very well be NSF purchased PI nights just using the existing instrument suite. And then, in addition, if PIs want to build instruments and bring them, those are nights that are open for them to propose for their instrument to go on the.
Okay, thank you.
Yes, Sunil, this is Lee. I had a question. These ideas about the involvement, you're putting these as ideas in the proposal? There's a little bit of flexibility here, right?
Yeah, and in the proposal, so it's an MRI proposal, so you can only talk about building it and commissioning it. You don't have to have a set operations plan. So I think what we want to indicate is that there are clearly options, and we will engage the community on figuring out which of these options, if any of them, are people want to do. And then we would, over the next couple of years, be writing proposals to try to realize one of these options. Okay. We've talked with the program officers, so they're certainly open to these options. But we need to demonstrate community interest in having these options available.
Okay, I have one more question. Sorry, Meredith. The proposal deadline is coming up. That's the immediate work. Are you also thinking about having some science white papers written for the February deadline for decadal?
Not really. I mean, this scale of, we're talking essentially about one proposal would get us out the door. So frankly, we're just kind of focused on the near term of getting that proposal funded and moving on. It just doesn't feel like this is the scale of project that needs a big push with white papers. And I expect that much of the science that we would do, that's already being talked about in white papers that other people are writing. So I welcome advice, but it's not clear to me that it's the most useful way to be spending our time right now.
Yeah, that's an important input. The group is spending a lot of time thinking about white papers. We've organized white papers for other, for the big missions, for other things that are coming up. But I wasn't sure if it would be helpful here also to see if there were people that are interested in writing white papers that would specifically be aimed at this kind of large area surveys from the ground and things like that.
Well, I could imagine a couple easy ways to do this. One is that, like I said, I think a lot of the science is probably being covered by white papers people are already writing. So if they can simply mention this as an interesting possibility for executing that science, and then maybe it does make sense for us to write a single white paper on the project itself, when the project white papers are due.
Right.
Like I said, I'm not sure for this level of funding it warrants a big push, but obviously any support that's out there will help the case as it comes to the review process.
Okay.
Part of it is just time. We have a proposal due in a week, and then there's another proposal due a month after that. So it's just not clear if we'll have the time to get those out. But if there are people who are willing to do such things, I'm certainly happy to support it and help in any way possible.
Mm-hmm.
Hey, Sunil, this is Neil. How does this play into or complement or relate to CCAT Prime?
That's an interesting point, exactly. Inevitably, there's some amount of overlap. I think one difference is the aperture areas are different. The confusion limits of the two telescopes are appreciably different. 6 meter to 10 meter gets you a gain. But I think another aspect of it is that we have many of the instruments ready to go and able to do science as soon as the telescope's built. And there's not just not just the existing instrument suite, but new instruments that are in the process of being built right now that are funded to be built. So I think we just have a strong case on the instrumentation, but yeah, I cannot deny that there's a little bit of overlap there.
So it sounds like it's more competitive rather than complementary from what you just said.
Yeah, I mean, you could make the reasonable argument that CCAP Prime is clearly the better suited for wide area surveys, given the large field of view, and that it would be silly for us to try to compete on that. But I think it's going to be a while. And as you saw, most of the science programs, there are large time surveys, but there's nothing that's basically, let's just do a massive many square degree blank field. There's the C+ survey, which is actually quite small in area, but it's the third dimension that's interesting there. And then for the clusters, it is single objects, going very deep on single objects. So we've tried to pick things that won't get eaten up by a telescope that has a very large field of view and can survey large areas. These are exciting projects that can be done with the field of view we have.
Sunil?
I don't think anywhere in the proposal we just kind of say, we'll do a continuum survey of many, many square degrees. There's just not a great, it doesn't jump out at you as something that's really the most exciting thing to do.
Sunil, this is Omid Noruzian.
Hi, Omid.
So I wanted to ask about the status of the paramps and also the prospects. What do you think really about the their prospects, and also are any of the science studies that you have now based on the paramps?
Right. So the current status is, as you probably know, part of the story. So Peter Day has a quantum limited version that is consistently quantum limited but very hard to fabricate. There's a new version that uses a new amorphous silicon that we developed that promises to be, or is much easier to fabricate, but it's still currently a few times quantum limited. But it's 6 months old, so I expect that that'll reach quantum limit on the timescale of the year. So I think the technology will be there, but yes, then someone has to figure out what's the exciting thing to do with that technology. Now, we haven't put much thought. We haven't. There's very little of the key science case that relies on the heterodyne instrumentation. It's mainly there as sort of a utility player for the PI fraction of the time. But with the paramps, we would be substantially more sensitive than APEX in a number of bands. And especially if you could build multi-pixel arrays of the paramps, galactic plane surveys in multiple bands, deeper than has been possible in the past, might be a very exciting thing to do. So we need to see how the technology comes along. I mean, I'd say right now that the heterodyne arrays that have been built, you kind of end up with a trade-off where each pixel is not as sensitive as a single pixel, and so the gain in mapping speed is it's appreciable. It's a factor of a few, but it doesn't open up a massively new window yet. So we need to see whether the technology opens up a massively new window, and if it does, then I think it's an exciting prospect.
Okay, thanks.
Yeah, and that kind of raises the point again about the technology. I mean, it really is all driven by what technology comes along, and that's going to create new science opportunities. If the super spec and time developments come along to the point that you can build a few arc-minute field of view focal plane at resolving power of 1,000, I mean, that's something that's never been possible before. And it's clearly something that you should do now as a lead into a future larger sub-millimeter capable telescope. Okay, it sounds like that covers it on questions.
Yeah, so I guess I'll just take the quick moment to say we can stay on this as long as Sunil wants to. People come up with some additional questions since we still have a few minutes before the hour. But thanks to everybody for joining us today. And just a reminder that we have these webinars basically every month, usually on kind of one of the first or second Tuesdays of the month at 1 p.m. Eastern time. So you yourself can give a webinar, or you can suggest webinar speakers. You can send that to any of us who are on the IR SIG Leadership Council. And thanks to Sunil for giving this great talk today. I don't know if there's.
So I had a couple further questions if we have a few minutes.
Oh yeah, of course.
Okay, so so one, certainly, even if you didn't feel you wanted to provide feedback on the phone, please send me email, especially on these ideas for the community involvement. You know, do these seem like reasonable options? Is the level of funding and the level of nights available a reasonable thing to ask? Are there other ideas for things that people would like to see? And then, you know, leading up to the proposal, and I think many of you got a similar survey when we did an MSIP about 1.5 years ago. I wanted to see whether there'd be interest in us running a small survey so we could just kind of be able to quantitatively state in the proposal level of interest from the community in the project. So I would put out a survey similar to the one we did 1.5 years ago, where basically we put the project summary up and we say, you know, is this a facility you would use if it were available to the community, should it go forward? And then we can just say in our proposal, you know, we got end responses positively on this idea.
Sunil, will the presentation be available?
Yeah, I can give it to Meredith, and I post it wherever you you normally post your webinar presentations.
Yeah, all of our webinar, the recordings and sometimes the slides, if they're provided to us, are posted on our IRSIG website. So that's pretty easy to find. I can post the address in the group chat window, and then everybody can refer to it there.
Yes, and I can link to it if we do set up this survey. We can link to it so that people can, in addition to the project summary, take a look at the slides again.
Thanks.
Yeah.
So I had another question, Sunil. Aside from the survey, which would be clearly helpful with the proposal, is there any other input or anything from this from this group that would be helpful in the near or midterm?
I think maybe, I mean, taking a look at that science table, and if you have any negative reactions to anything there, that would be very welcome. At this point, I don't think I have enough time to process new ideas, but yeah, feel free to send them along, because in addition to this proposal, which is due in a week, the mid-scale RI pre-proposal is due in a month and a week, so there is opportunity to improve and revise things. So any input on ideas, either, you know, critiques of what's there or other new ideas that kind of fit within the parameters we've talked about would be very welcome. And just any comments overall, anything that jumps out at you as a worry that hasn't been talked about that we should make sure we address in the proposal, any arguments you can think of that we haven't already made in favor of the idea. So any kind of comments at that level. I just have a limited ability in the next week to really make any substantial changes to the proposal.
No, yeah, I was really thinking about sort of between that and the next milestone.
Yeah. Yep.
I think you would be able to work on input. About you said something about the remote observing. Is your idea that at the new site that you know, if there were some PI nights available, like you mentioned, that this would be remote operated, and where would this happen from?
Anywhere. When we were running the CSO in the last 2 years, we had people observing from Pasadena at home. We had people observing from Korea, from China. I mean, it really had been set up very nicely so that you could do everything from your from there. You know, there were static you know, screens that you could log into that would keep all the important windows up, and you could just do it from your laptop at home. So it's essentially a zero cost observing.
So it's even simpler than using Keck or anything like that remotely.
Yeah, you don't even have to, you know, you don't have to go to the Keck observing room in Cahill. You can literally do it from your home. And trust me, we did this because we didn't have any money at the time. We would have one person on shift until about midnight Pasadena time. And then we would actually let the macros just run independently for a few hours, and then someone would get up at 3 or 4 in the morning and watch it and complete it and shut down and close the dome. And it worked very well. I think there was only one time in about 1.5 years that Simon Radford had to actually drive up to fix something because the dome wouldn't close. And you have to remember okay, maybe we're getting into minutiae, but that dome was never designed for that remote operation. Part of what we're having M3 do is to essentially design a completely foolproof scheme such that even if you lose power and you can't go to the site, the dome rolls closed and protects the telescope.
Mm-hmm. Yeah, that seems that. I mean, I guess I didn't realize that, but that makes it sound really interesting and really very much more, even more available than what people think of when they think of remote observing. So.
Yeah, and yeah, I know there's a history with the CSO of lots of fiddling with receiver tuning knobs, right? But with these new tunerless receivers and synthesized LOs, all the heterodyne receiving is also heterodyne observing is completely remotely operable. You don't have to be going to the telescope, going out in the side cab, checking things out.
Well, so I think if that's all the questions we have, we're just about at 2 o'clock. So thanks to everybody for joining us today. I posted the link to our website in the group chat window, which you can find clicking at the bottom of the Zoom screen. So we'll post the recording of this and the slides possibly, and we can distribute a survey if Sunil puts that together later. So thanks again to Sunil, and thanks to everybody for joining us today.
Okay, thank you for the opportunity.
Thanks.
Bye.